Hello everyone! In this video we're going to look at the problem in which we need to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. So the curves we're given are sine of x and cosine of x, and the region will also be bounded by this interval, and the region will be rotated about the line y equals -1. We're going to start by sketching the given region, so let's call it step 1. Step 1, sketch the region. And while I'm calling this a sketch, I want it to be as accurate as possible. Okay, so I'm given two trig functions here. They're basic sine and cosine functions, so that means that to sketch the region, I'll just use the basic key values from 0 to 2 pi. So I'll use pi over 2, pi, 3 pi over 2, and then 2 pi. So we know that graphs of sine and cosine basic functions will lie between 1 and -1. And now sine function, that's the one that starts at the origin. Then it goes to the maximum value at pi over 2, it's at 1. At pi, it's 0. At 3 pi over 2, sine is -1. And at 2 pi, it's 0. Okay, so here's that wave. And now cosine function has value 1 at 0. At pi over 2, it's 0. At pi, it equals -1. At 3 pi, it's 0. And at 2 pi, it's back to 1. Okay, so that one was y equals sine of x. And now this wave represents cosine. It's also given that the region is bounded by 0 and pi over 4. Okay, so if it's pi over 2 here, pi over 4 will be the midpoint. And we also know that value of sine and cosine at pi over 4 is the same, right? It's radical 2 over 2. So it means that, well, that's going to be that point of intersection. Now, since my region should be bounded by 0 and pi over 4, 0, pi over 4, well, it has to be this one over here, right? Now, once I sketch the region, next step will be to rotate that region about the given line. So y equals -1. So I will be rotating it about this line. Y equals -1. It's the horizontal line that goes through -1 on the y-axis. And here I can see that my region turned out to be pretty small, and when that happens, you want to redraw it and make it larger, because you need to see all the details when you proceed with the method. Oh, and by the way, the method that we are using for this example is the washer method. Okay, so step 2, sketch the solid. Now, if region is large enough, I can do it right on this graph, but once again, in my case, I will enlarge it. So the only part that I worry about is this one here. So I'll sketch like this. I know I'll be reflecting it or rotating it about y equals -1, so I will have more below, so I don't need much space above here. So I'll say pi over 4 in my new sketch is right here, so I will enlarge the scale. And that's +1. So -1, let's say, is here. -2, -3. Here's the line about which I will be rotating. Y equals -1. And now let me try to recreate this region. I'm doing just this part. So I'll need to place this point of intersection and add the curves. So let's say that's the point of intersection. So right here I'll have, that's the bottom function is y equals sine. y equals sine of x, and then the top one that goes like this is y equals cosine of x. Okay, so here it is. And now let's rotate. So when you rotate the region, and if you're doing this by hand, what do you want to do? You want to start by reflecting this region over the axis about which you're rotating, or the line about which you're rotating. So if I reflect this region, because as I rotate it, well, it will appear down here, right? Okay, so this is about how it's going to look. And now once you reflected the given region about the line of rotation, then you want to add some curves so that you can kind of see that it's a three-dimensional object right now. And what I like to do, not to overwhelm my picture, I like to add some curves on each end of this solid. So here I will draw like an oval. That now I can see that, creates this hollow space inside the solid. So inside here I also have a hollow space. Now that's the front surface, and back there I'll have the back surface like that. So just adding those ovals on each end, on the right or left, or top and bottom, depending on how you're rotating, it creates this three-dimensional object, or it starts looking like 3D object. So hopefully you can see that. And that's all I want to add as far as creating the solid. But what I'll do next, and that's actually step 3, and it's very, very important step, I'm gonna draw a sample washer. Okay, so what is the washer? Basically that's how the cross section of this solid looks like, right? If I slice it, then this is what I'll see. I'll see a washer. Let me draw it. I'm going to use different color. So that's the outer edge of the washer, and it's going to be this, it's going to have this empty space inside. We'll just use solid lines. That's okay. So why is it important to look at the typical washer? Well, because the integral that we'll use to find the volume will be set up based on the way the washer is positioned and based on its outer and inner edges. So I'll say step 3, and it's important step. Well, they're all important, but sometimes step 3 gets skipped and things go wrong. So it's an important step to have. Draw a typical washer or disc, right? Once you have the picture of the typical washer, then you're going to take a few more very important steps. So step 4 will be, it's super important one. You will need to determine whether you're going to integrate with respect to y or with respect to x. And that's where a lot of mistakes happen. So how do you know what is the right variable for the integration? Think this way. This is a typical washer and I position it here, right? Did I have to put it right here? No, I could place it in a different spot. Well, where exactly? Well, I could position it a little bit closer to the right side, or I could position a little bit closer to the left side of this solid, right? And depending on where I put it, the washer itself changes, right? We can see that if we move it to the right, its outer edge gets smaller, but its inner circle or this empty or hollow space becomes larger. But as we move it to the left, the washer itself gets larger while this inner hole gets smaller, right? So its size changes as I move, or as I choose position of the washer moving right left. So along which axis do I move when I move right left? Well, that's when I move along the x-axis. Oh, I didn't even made it here, right here. That's the x-axis. So as I move right left along the x-axis, washer changes. It means that its size depends on where it's positioned along the x-axis, and that means that the variable x plays the role here. And if the x variable plays the role, well, we have to integrate with respect to x. So everything depends on x in this case. That's this right-left motion. So step 4, determine the variable of integration. And we said integrate with respect to x. Now, just a side note, if our washer was a horizontal one, if it was going this way, then we would see that it had to be moved up and down, and then some size changes. So that's where everything depends on position along the y-axis, and everything depends on y. That's when you integrate with respect to y. So that's how you will check that in step 4. Once you figure out and determined what's going to be the variable of integration, you're ready to set up the integral. So step 5, set up the integral. And that's important to do those steps in this order, because once we know the variable of integration, now we know that as we set up the integral, everything should be in terms of x. I shouldn't see any y values. So to find the volume of the solid, if we use the washer method, the function that we're going to be integrating is the function representing the area of this washer, of a washer. So basically, when we're integrating, it means that we're adding infinitely many areas of infinitely many washers that we can kind of like find here as we slice this solid. How do we describe the area of the washer? Well, washer, if I look at it from above, it looks like this, right? And it's area found by, area of the washer, by taking the area of the bigger circle, and we say that it's pi r squared, where r is the outer radius, minus the area of this inner circle, pi r squared inner. Just to remind you where that formula comes from. And when I set up this kind of expression, of course I can factor out pi, and it's just r squared, where r is the outer radius, and then minus r squared, where r is the inner radius, like that. Okay, so that's what I'll need to find, but of course those r's will have to be expressed as functions. And that's going to be next step. Well, I'm saying step 5, so I guess it's within step 5 for us. How do we determine outer and inner radius? Well, that's why having large picture is very important, and that's why having the washer in front of you is also very important. So what I'll need to do is to show both outer and inner radii on the sketch, on this picture. So where is the outer radius? So the outer radius will always, well, as any radius, it will connect center of the circle with the circle itself. So centers for both inner and outer circles are on this line about which we're rotating, right? So here's the center for both of them. Well, if I take the center and connect it with the outer circle, and when I do that, I always want to go in the direction of my original region, then that's going to be the line. I'll try to make it a little bit thicker, right? So from here to here. And now my goal is to describe this line, well, in general. How do I describe it? Well, I can see that this line, well, actually it's a segment, right? This segment consists of 2 parts. It has this part. What is this part? Well, this part is from the x-axis to the function, or to the graph of the function. What function is it, by the way? Well, it's cosine function. So how do we describe segment that stretches from the axis to the function? Well, it's described by cosine of x, right? The general way of describing it is cosine of x. But I also have the second portion. And what is the second portion? Well, the second portion actually does not change its length no matter where I pick this washer, this arbitrary washer. It's always going to be 1 because the second portion right here, it goes from line y equals -1 to the x-axis. So it's just exactly 1 unit. So altogether, this outer radius will be expressed by cosine of x plus 1, or 1 plus cosine of x, either way, right? Cosine of x is this part, 1 is that part. Now let me try it with the inner radius. Inner radius, and now my picture is getting a little bit messy, but hopefully you can see what I'm doing. Again, I'm starting at the center of the circle of the washer, and I'm connecting the segment with the inner circle, right? So that becomes inner radius from here to here. Now, how long is this arbitrary segment? How do I describe it in general? Same story, from the x-axis to this line, it's going to be expressed by sine of x from here to here. And as I move right, left, this portion gets smaller or bigger, and well, that's how it's described, sine of x. But now I have this additional part over here that also equals 1, and it's always going to be 1 no matter where I place the washer. So altogether, this segment is described by sine of x plus 1. That's going to be our inner. Sine of x plus 1. Okay, so that's why it's important to have large picture and washer and both radii be in front of you. Please don't skip that step. Okay, we're ready to set up the integral with that. So we got this part, well, we know both radii, we just have to square them as we set up this function. Here's the integral. I'll need to also go back and add the limits of integration, but this pi I will actually place outside since it's a constant. And inside here I will have, let me use brackets, I will have first the outer radius squared, the outer radius right here, cosine x plus 1. I have to square it, right? Outer radius squared, minus the inner radius squared. In this case, it's sine of x plus 1 squared, dx, right? And we're integrating with respect to x. So we got that part. Let's add limits of integration. This is how I figure them out. So first of all, since I'm integrating with respect to x, the limits of integration should come from the x-axis. And the way I think about it is, as I take this washer and or think about other possible washers and I move right, left, what is the leftmost position I can place it, and what is the rightmost position I can place washer along the x-axis? Well, I know I have to stay within this region, right? So that means that the leftmost place is at x equals 0, and the rightmost place for arbitrary washer is at pi over 4. Right? So this region goes from pi over 4, from 0 to pi over 4. And that's going to be, these are going to be the limits of integration from 0 to pi over 4. They come from the x-axis. Okay, so we are ready to integrate, but I just want to emphasize that up to this point, all those steps are super important, because if this integral is not set up correctly, well then, even if you integrate it correctly, the answer is not going to be right? So don't skip anything here. And step, well, if we go in order, let's do step 6, integrate. Okay, so I'll continue, and I can see that before I actually start integrating, I would want to simplify expression here as much as I can. So what I'll have to do, I'll have to square those two expressions first. So if I square cosine of x plus 1, well, it's same as cosine x plus 1 times cosine x plus 1, which as I FOIL, I'll get cosine squared of x plus 2 cosine x plus 1, or I can use square of a sum formula, minus, and then for now I'll use parentheses here. Then as I square sine of x plus 1, again, I just have to write it twice and FOIL. Then I'll have sine squared of x plus 2 sine x plus 1. Okay, and then dx. Now as I clear the parentheses, the signs will be minus and minus. So I can see that positive 1 and that negative 1 will cancel. So I'll have pi integral from 0 to pi over 4 cosine squared of x plus 2 sine x. Now minus sine squared of x, and then minus 2 sine x dx. Okay, so now we're ready to integrate, but let's think about what we can do and what we cannot do yet. So I have no problem. Oh, that's cosine. I have no problem to integrating this cosine. It's just the basic integral, right? And sine. Those two are not the problem. I have cosine squared of x and sine squared of x. So these are not basic integrals since they're both squared. It means that I have to be creative, and one way or one thing I can do here is to recall that there is a formula that we learned in trigonometry that tells me that when I put them together, well, it's not formula, or it's identity, right? Cosine squared of x minus sine squared of x, that's an identity that equals to cosine of 2x. It's a double angle identity. And that's what I'll do. So we'll just have to do some trigonometric manipulations here. Now this is what I'll have. Pi integral from 0 to pi over 4 cosine of 2x plus 2 cosine x minus 2 sine x dx. Okay, and now all that we should be able to integrate. For this first term, cosine of 2x, as I integrated, technically I have to apply very basic substitution rule. I'm gonna skip that since it's very basic, but if you want to do it on a side, you just have to let u be equal to x. So that's going to be the substitution, u equals to x. But what we end up with, let me start writing it. This basic substitution rule that we apply will just end up with the extra coefficient 1/2 in the front. So integral of cosine is sine, so it's going to be sine 1/2 sine 2x plus 2 sine x, and integral over antiderivative of sine is negative cosine, so it's going to be plus 2 cosine x evaluated at 0 and pi over 4. I guess I should say pi over 4 and 0. Okay, now I will plug in pi over 4, so I'll have 1/2 sine of 2 times pi over 4 plus 2 sine pi over 4 plus 2 cosine pi over 4, and then minus. Now all that have to be also evaluated at 0, and I'll have to use parentheses since I'm subtracting. Minus 1/2. Well, as I plug in 0, it's going to be sine of 0 plus 2 sine of 0 plus 2 cosine of 0. Let's see. Now sine of 2 times pi over 4. 2 times pi over 4 is pi over 2. We know that sine of pi over 2 is 1. So here we'll get just 1/2 plus 2 times sine of pi over 4 is radical 2 over 2 plus 2 times cosine of pi over 4 is also radical 2 over 2 minus, what do we have here? We know that sine of 0 is 0. That's gone. Another 0, so that's gone. And then cosine of 0 is 1. But now 2 times 1 gives me 2. And I also have minus in the front, so it's minus 2. Okay, so what's left to do is just to do this computation. We'll have 1/2. That cancels, so plus radical 2 plus another radical 2 minus 2. That is pi. Let me just put everything, bring everything to the same denominator. So I'll do denominator 2. So it's 1/2. Now this is 2 radical 2. But if I want to combine them, I'll write it as 4 radical 2 over 2. And that is minus 4 over 2. Okay, so we're almost there. Pi times, let me start with this, 4 radical 2, 1 minus 4 minus 3 over 2. So that represents the volume of that solid, and when I am looking at the final answer, I want to make sure that's a positive number. Well, here I can see it's going to be a positive, right? Because 4 times square root of 2, it's going to be more than 3. So I will get something positive. That looks good. And once again, to recap the important steps, let me go back to where we started. So important steps are, 1, to have large pictures, large solids, so that you can see all the details. To sketch the typical washer, sketch on outer and inner radii, so that you can see how they should be described. That's usually where most mistakes happen. And after that, oh, and then of course determine the variable of integration, right? Just move the typical washer along that solid, and it's going to be intuitive which way you have to move, right, left, or up and down. So I don't think you're going to make mistake with that. But if you're moving along the x-axis, integrate with respect to x. If you find yourself moving that typical washer along the y-axis or up and down, well, integrate with respect to y, and then have only y everywhere in the integral, including the limits of integration. They also should come from the y-axis. Okay, so that's how you find the volume of the solid using the washer method.